All right, welcome everybody. Today is lecture 20 in our lecture series on pattern recognition, and this is what we are going to study today in in 3 words I should say. It is about the kernel trick. And I will first generally and gently expose ourselves to the general idea here, and then I will ever so briefly talk about kernel engineering, and then I will ever so briefly talk about a couple of kernel algorithms, some of them to a larger extent, some of them to a lesser extent, and towards the end of today's lecture I will talk about something that is really cool about this idea of kernels. And you have already guessed from the way that I say, I will gloss over kernel engineering and some of the kernel algorithms. The reason for that is that our menu for today is once again actually a menu I should have spread over 2 lectures. But once again I squeeze all of this into just 1 lecture, and a lot of the stuff is really again just algebra, so I'll really gloss over that. And then also some of these things are not of utter major importance, but it is good to know about these things, and it is good to have a reference. So if I'm a bit sloppy or quick, say with respect to kernel linear discriminant analysis, then don't worry, that is more or less by design, but all the details will be on the slides anyway. All right, let's go. I will start with this outrageous claim that there are situations where high dimensionality can be a blessing. And of course you are nodding, you know that these situations exist. Nevertheless, this appears to be an outrageous claim because a couple of weeks ago I spent a whole lecture on illustrating the problem of high dimensionality, and actually it has this name, the curse of dimensionality, and then we talked about what to do about it, and now it appears as if we were sort of turning things upside down, claiming the opposite, that high dimensionality can be a blessing. This is nevertheless really easy to be seen, and we have transparency problem again. Do you remember? It was in our 7th or 8th lecture, I don't recall which one exactly, where we talked about least squares techniques, for instance for linear classification. And we looked at least squares for binary classification of linearly separable data, and we looked into least squares for multi-class classification of linearly separable data, and then I talked about the case where the data was not linearly separable, and I said, well, we can transform the data and then perform the classification on the transformed data and back transform the results we get. Here is another instance of that problem. On the left hand side we see a binary classification problem, say, obviously 2 classes of dots, as always, a blue and an orange class of dots, and there is no separating hyperplane between these 2 classes of dots. That is, if we treat this as a binary classification problem, like say a new dot comes in, probably over here, and we want to say, is it a member of class blue or class orange? It is a binary classification problem, but it appears as if linear techniques would not help us any further here. And of course, that is very true. Like in 2 dimensions, there is nothing we can do in order to treat this problem as a linear classification problem. However, to the right, I've shown you a crazy, more or less crazy transformation. This is again a didactic example. So a crazy transformation that takes as input a 2-dimensional vector and produces as output a 3-dimensional one. So this x here is the input vector that appears to remain untouched. And the 3rd argument is the squared norm of the input vector. This is a mapping from R2 to R3. And I have designed this mapping deliberately. If I were to apply it to all the data in this example, what we get is the distribution, three-dimensional distribution of data shown on the right. Once again, when I upload the slides, you can actually see through this plane I have drawn in between the two classes. The effect of this transformation is that the orange points will be assigned a x3 coordinate, a three-dimensional coordinate, that has much higher values than the third coordinate for the blue dots will have. And once we apply this transformation in this silly didactic example, it is actually possible to fit a now two-dimensional hyperplane in between the two classes of transform points. And that goes to show that this original non-linearly separable two-dimensional problem becomes linearly separable in three dimensions if we can choose a clever transformation of the data. Well, now that seems to be an obvious thing. It appears as if there is a transformation that will do the trick. Here is another example of an original two-dimensional problem that is not linearly separable. This is a noisy instance of the XOR problem. There is no single line or hyperplane in two dimensions that would separate the class of blue dots from the class of orange dots. There could be two such hyperplanes and then we would be good, but if we were just after one hyperplane, there's nothing we can do in two dimensions. However, we can again try to come up with a transformation from this lower dimensional space R2 to this moderately higher dimensional space R3. This time I'm defining the transformation like that. Is basically to say, is again a transformation that takes a two-dimensional vector and produces a three-dimensional vector. And the first two dimensions in the resulting three-dimensional vector are again the original coordinates of the vector we pass as an input. And the second, the third coordinate is basically the distance of all the points to this diagonal, and then again we square this distance so we get this crazy valley-like thing, and again we cannot see the blue dots which have vanished under this hyperplane. But once again, in three dimensions, using this transformation, it is possible to fit a separating hyperplane between the two classes. So in three dimensions, we can deal with these classification problems using any of the methods we have studied earlier. Well, that is good, but the general problem is that, I'm so much ahead of myself. So once again, the general idea is it probably possible to map data from a lower dimensional space, in general lowercase m dimensional space, to a higher dimensional space where let's indicate the dimension of that higher dimensional space using capital M, and let us assume that this original space is of a much smaller dimension than the new one. So it seems to be a good idea in certain situations to transform data to higher dimensional spaces, which then is to say that we can deal with these kind of nonlinear problems using our linear techniques. And I have already hinted that it was lecture 8, now that I see it in lecture 8. Crucial observation is that really most of the methods we have studied so far are at their heart linear algorithms. All the classification ideas we had so far, least squares, linear discriminant analysis, support vector machines, require us to compute an inner product between a weight vector, say, and an input vector, and threshold that. But at the heart of these algorithms is the idea of an inner product, which is a linear operation. And we also looked at nearest neighbor classifiers and k-means clustering, where at the heart of these algorithms is the problem of computing Euclidean distances, which is at first sight something that is a not a linear operation, but we can actually break it down into a series of linear computations. So the Euclidean distance between any vector x and the vector q is actually the inner product of the vector x with itself minus 2 times the inner product of x and q plus the inner product of vector q with itself. So even though this looks like a quadratic operation, and it is, but we can express it in terms of inner products anyway, and that is to say this would require us to compute 3 linear operations. So at their heart, all the methods, or I should say most of the methods we have studied so far, deal with inner products, linear operations. And the idea therefore could be that if we were to deal with a problem that is non-linear, just by looking at it in 2 dimensions we can easily recognize that, is to say, well, how about we would really map the data we are given, so the training data we are given, just as well as the data we consider in application. We would map all the data from a lower dimensional space to a higher dimensional space. And typically these higher dimensional vectors are written in terms of the transformation we apply. So whenever we see this phi of x from now on, this will actually indicate a capital M dimensional vector. Right? And if we then have transformed the data to this higher dimensional space, well then we might learn a projection vector omega is different letter than the W, just to indicate that this will be a different vector. A capital M dimensional vector omega, and use that one to solve our, say, classification or regression problem in this transformed space. And of course we might then again threshold this, basically instead of computing a function y of x, we could say let's look for some function h of x, just a different name, which is to say we first transform all the data into a high dimensional space, and use all the training data to determine an appropriate projection vector omega. Once we have that, we can actually apply it to compute, I don't know, say the classification problem or the regression problem we are interested in. This is the general idea, but there are a series of problems when it comes to this idea. From the 2 silly examples we've seen earlier, it is already apparent that it may not be a triviality to come up with an appropriate function phi that maps the data we are given into another representation. It appears as if that function phi crucially depends on how the data are distributed in the space they are given. Let me once again, so for this situation here, we have basically a circle and a blob, and this transformation worked well, and in this situation we had to use another transformation in order to have the data become separable in a higher dimension. And the question is, of course, what, if anything, could we say about how these transformations phi would have to look in general? That is a crucial problem. A more practical problem may be that even if we could decide or answer that question, like how would such a transformation have to look like in general, it might be very, very expensive to compute that. Now in our silly examples, once again 2-dimensional data, a mapping to 3D did the job, but what about if the data were 1000 dimensional and we would have to map it to a 1,000,000 dimensional vector space, some crazy nonlinear transformation. All these transformations were nonlinear. Right? Some crazy nonlinear transformation of 1000 dimensional data, map it into a 1,000,000 dimensional space, and there it would be separable. Well, then it might be actually very, very expensive to transform the data. And even if that is not so much of a problem, if we have to compute inner products in a 1,000,000 dimensional space, well, of course, this is not really a problem, but if we have to process millions or billions of data, then even silly inner products, if they require summations over lots of products, millions of terms, become costly. So these are three challenges. The first one is a very principled one, and the second and third are rather practical challenges. And the question is there something we can do about this? And it turns out there is. There is something that is called Mercer's theorem. And I will spend some time out of all the stuff I'm going to talk about today on trying to hit this really home. What is the underlying theory here? So let's go for it. The next couple of slides might be a bit abstract, but if there's any problem, please ask. I will begin with a definition. So no example to warm up here, but let's dive right in. A Mercer kernel is a symmetric, positive, semi-definite function, let's call it lowercase k, that takes two arguments, and these two arguments are m-dimensional real vectors, say. And this is a function from Rm times Rm to the reals. And it is a function such that, once again, we have a function k of two arguments x and y, and it is supposed to be symmetric, so k of x and y must be the same as k of y and x. And this is crucial, and we will not understand it right away, but in about 10 minutes we will. This Mercer kernel can be understood as an inner product of two possibly very high dimensional vectors. So we are given two vectors x and y, and there is some function k that is symmetric, and the value of that function k of x and y can be understood as the inner product of phi of x and phi of y, where phi of x and phi of y might be very high dimensional vectors. Another thing that is important here is this notion of a positive semi-definite function. And a positive semi-definite function is a function where if we are given some function g of x, where again this x is an m-dimensional vector, and we look at the inner product of this function with itself, and that inner product evaluates to something larger or equal than 0, then that implies that if we look at this crazy double integral, g of x times function k of x and y times g of y, and we integrate that with respect to x and y, then that would evaluate to something greater or equal as well. Now, before I continue, do you remember that in one of our very first lectures, when we familiarized ourselves with the notion of a vector space, I said that vector spaces are a dime a dozen. Euclidean vectors are vectors, matrices are vectors, and I said that functions over the reals are nothing but vectors. This is not how we are used to think of them, but functions like g of x have all the properties we would require for things we call vectors, that is, elements of a vector space. And in particular, I said that there are inner products between these kind of vectors. And this is really just to say that we look at the integral of a function times another function and evaluate that integral. And therefore, this integral g square of x is really the inner product of the function g of x with itself. Now, this all looks crazy, but we will see in a second that this is indeed just a generalization of something we are more or less familiar with. This just generalizes in the same way as function generalizes the notion of Euclidean vectors. This just generalizes certain properties of Euclidean vectors to the case of functions as vectors. Namely, this notion of a positive semi-definite function generalizes the idea of a positive semi-definite matrix. Look, when it comes to matrices, say K, we say a matrix is positive semi-definite if, well, in a product of two vectors, of a vector G with itself will always be in Euclidean vector spaces something greater or equal than 0. So this thing here is given for this vector G. We say that this matrix K is positive semi-definite if the product G transpose times K times G, which is of course this sum over all the I and J, Gi, Kij, Gj, if this evaluates to something greater or equal than 0. All right? And look at this. This product that defines, we look at when we define the notion of positive semi-definite matrices, is this double sum over all the components of G, then the components of matrix K, and all the components of G again, this time with index I. This is really generalized by this expression where the sum becomes an integral. The sort of components of G with respect to index I become function G of X. The components of G sort of with respect to subscript J become G of Y. K of I and J becomes K of X and Y. And we do not sum over I and J, but integrate over X and Y. So this really just generalizes this notion of a positive semi-definite matrix from finite dimensional vector spaces to infinite dimensional vector spaces of functions over the real. And a very important thing we know about positive semi-definite matrices is that they have orthogonal eigenvectors ui and positive eigenvalues lambda I, which is to say that if we look at this equation and there is a vector ui and a scalar lambda I, such that matrix K times vector ui equals scalar lambda I times vector ui, which is, this is what defines an eigenvector and an eigenvalue of this matrix. But we know that positive semi-definite matrices will have eigenvectors and eigenvalues. And we actually know, for the case of positive semi-definite matrices that have this property, that the eigenvalues will all be greater or equal than 0. And in analogy, a positive semi-definite function has eigenfunctions and eigenvalues. And that is to say, look at this, if we have a matrix vector product in terms of functions as vectors, Hilbert vectors I should say, this becomes an integral over this function. This function now assumes the role of the matrix, and this function here assumes the role of the eigenvector. But since these are functions, we say this is the positive semi-definite function and this is the eigenfunction. And instead of summing over all the entries, instead of doing this kind of operation, we have again an integration here. But the value of this integral, k of x and y, times psi of y dy, is just a multiple of this function psi I of y. And this scalar mu I is called an eigenvalue. Right? And those of you who have been with me in image processing, where we study the notion of the Fourier transform and this notion of eigenfunctions and orthogonal functions and so on, for those of you, this is quite normal. For those of you who have not been with me in image processing, let me point out this crazy fact here. that whereas the eigenvectors and eigenvalues of finitely large matrices are of course of finite dimensions, and there are finitely many of them. For this generalization we are currently looking at, these positive semi-definite functions will have infinitely many eigenfunctions and eigenvalues. But this is really just because this generalizes these notions we are familiar with from the field of linear algebra to infinitely dimensional vector spaces. And so therefore there will be infinitely many eigenfunctions and eigenvalues. And these eigenfunctions are orthogonal just in the same sense as two Euclidean vectors are orthogonal. If we look at the inner product of two eigenfunctions of this operator or Mercer kernel, then it will evaluate to delta ij, which is to say this will be 1 if j equals I, and it will be 0 otherwise. So once again, this is an inner product between two functions, and if both these functions are the same and they are eigenfunctions of an operator, then this inner product will evaluate to 1, and if these two functions are different eigenfunctions of the operator, then they are orthogonal, and the inner product will evaluate to 0. And we can carry on with these analogies, and I could make all of this extremely precise, and again I'm not. Right? I'm just sort of trying to convey some intuition here in analogy to the spectral representation of a matrix, where we say that we can understand the matrix K, if it is positive semi-definite, as the sum where I ranges from 1 up to m being the dimension, K is a square matrix, so being m by m matrix. K can be represented as the sum over all the eigenvalues times the outer product of the eigenvectors with themselves. This is again something we are well familiar with from linear algebra. This extends to these crazy operators in infinite dimensions, or like these functions. We can say that this function k of x and y can be represented as an infinite sum over the eigenvalues times, well, there is no real outer product here, it's just the product of the eigenfunctions with themselves. And this then leads to Mercer's theorem. It's of considerable importance in functional analysis, and for about 20 years of great popularity in machine learning and pattern recognition. It says that for every positive semi-definite function k of x and y, there exists a vector value function phi of x, such that we can express k of x and y as the outer product of two vectors, phi of x transpose times phi of y. And let me prove that to you, and that is done quickly because it just recaps what we discussed previously. On the previous slide we said that a positive semi-definite function can be expressed as the sum over its eigenvalues times sort of the product of the corresponding eigenfunctions. Now then I could put a square on the mu I to turn one mu I into two of them, right? And then I could say that square root of mu I times psi I, let's call that phi I. So this expression via this trick here becomes the sum over the I phi I of x times phi I of y. But this is what we call an inner product. So there you have it. This is Mercer's theorem. what does that have to do with our problem? We said we might be interested in a transformation phi that takes a vector we are given and maps that to a high dimensional space and do computation in that high dimensional space. And I said it may not at all be obvious what kind of function phi to choose. Now we have learned all that we are after is inner products between these phi's, right? And now we have seen that we can think of these kind of inner products we are actually interested in high dimensional spaces, because we want to do analysis in high dimensional spaces to solve a lower dimensional problem that is nonlinear. But we have seen that these inner products, if we are lucky, can be expressed like that. So it's still not clear that we can really do this, but it hints at the fact that it might not be necessary to compute these kind of inner products. Instead, there might be a function, k of x and y, which we can use instead. And that is then again to say we do not have to worry about choosing these transformations phi. Maybe we have to worry about choosing this function k, but one worry is gone and we have replaced it with another. And this is beneficial because the previous slide told us that we really do not have to compute these inner products, which I said might be expensive if these are million dimensional vectors. We can, instead of computing these inner products, compute these kind of functions. Yeah, that is that. And what does that tell us with respect to the problem we are dealing with? It can be summarized in this notion of the kernel trick. And this is important. And I want you to take that to your hearts. We have not seen this in practice yet, but we will in a couple of minutes. But a take-home message already at this point is the notion of the kernel trick. And that is to say, the kernel trick is first to rewrite an algorithm for data analysis or classification in such a way that input data x only appears in form of inner products. That seems to be doable. I said many of the algorithms we studied so far are of that nature. And second, and this is now the real kernel trick, to replace the occurrences of these inner products by kernel evaluations. So the kernel trick is, if we're given some algorithm, maybe we can rewrite it such that really the input data x only appears in terms of inner products. And if that is the case, we then replace the computation of inner products by the evaluation of kernel functions. If we can do this, then we can deal with nonlinear problems using the linear algorithms we have studied so far. Right? Okay, all of this was very abstract, and so we have to make it slightly more concrete. And the obvious question is, well, do these kernel functions exist? I mean, how do they look like? Is there something we can understand as a kernel function? And yes, there is. The inner product between x and y is a kernel function, which is to say, if we consider a transformation phi of x equals x, that is the identity mapping, then phi of x transpose times phi of y, which would then be x transpose times y, is a kernel function. It's not of much use, but it is proof of concept. These things exist. This is good to know. This is good to know. They are there. This one is, of course, we have worked with this all the time. No apparent benefit of looking at this crazy transformation, phi being the identity, but it is indeed, if we look at the inner product of identity transformed vectors, the result is a kernel function. It is symmetric and positive semi-definite. And now, really ever so quickly, for For the next slide, I will assume that x and y are m-dimensional vectors. Then there might be a couple of constants, all of them real values, larger than 0. Some function, I don't really care about this function. And let's also assume that there is some valid kernel already. Right. Under these assumptions, we can actually come up with infinitely many kernel functions. We can, for instance, say that if k1 is a valid kernel function and c is some constant greater than 0, then c times k1 will be a kernel. If there is some function g whose inner product evaluates to something greater than 0, and k is a valid kernel, then this will be another valid kernel, and so on and so forth. So if we look at the inner product of x transpose and y and add some constant to it, that will be a kernel. Interesting kernels are also these polynomial kernels, where we just look at the inner product of x and y, add something to that, and raise that to some power. And this one's called the Gaussian kernel. It's also of great popularity and importance. And these are just really a few examples. There are infinitely many kernels out there. And I really have to stress the following. We are given data, x and y, say, in a lowercase m-dimensional vector space. And these data enter our computations in form of inner products. And we then replace those inner products between x and y by evaluations of kernel functions, which we now understand. K of x and y is the same as phi of x transpose times phi of y, some transformations of the data we are given. These functions, these kernels k, always can be understood as inner products in some high dimensional space. And what that means is shown here. For this inhomogeneous linear kernel, we have the inner product of x and y, the data we are given, and just add something to it. That is the same as if we were to compute an inner product in an m+1 dimensional space. If we look at these polynomial kernels, inner product of x transpose and y plus some constant b raised to some power d, then one can show that this is the same as if we were to compute an inner product in an m plus d choose d dimensional space. So depending on our choice of d, that can become a very high dimensional space. And actually, if we look at this Gaussian kernel, where we basically compute the distance between x and y squared, divide that by 2 some sigma square, has the same role as variance in a Gaussian, and the e to the minus this expression, this actually really corresponds to an inner product between two vectors in an infinite dimensional space. And I will keep it at that and just point out that to understand and to make sense of all of the above, please, I urge you, read these 2 lecture notes.
And not the second.
Pardon?
Why not the second?
Because it's not there yet. The content of the second will what is to come next, actually, will be what's to come next. But this one explains this notion of a Mercer kernel and how a positive definite function generalizes the notion of a positive semi-definite matrix. This is in this first note. And this one here explains why all of these things are valid kernels, how we can, given one kernel, and we are given one kernel, this one always exists, how we can sort of use inductive arguments to create more elaborate kernels out of that. And in particular, it explains why these ones correspond to kernels or to inner products in very high dimensional spaces. So this outrageous claim that this here is an inner product in an infinite dimensional space is explained in that note 3 here. All right, and I will keep it at that because there is way more interesting stuff to look in, namely, namely, what does all of this mean for practice? Like, how can we now actually really use that, and what cool effects does that have? And I will now discuss how to kernelize many of the algorithms we have studied earlier. And I will start not with the most obvious one to kernelize, but with the easiest one we studied. And the easiest one we studied was the problem of determining, say, a weight vector W using least squares. And we saw how to use this for regression problems and for classification problems. Right? The idea is that we are given some data X and labels Y. And I will assume that we, for the least square setting, once again resort to this trick that we extend the dimension of the data we are given by one dimension that will always carry a value of 1, and that the corresponding weight vector will of course also have an additional dimension which carries this W naught, this bias or offset. So I'll squeeze that into one vector. And if we're, in this general setting, we're given data vectors xi with corresponding labels, either some function values we wanted to do regression with, or some pluses or minus ones, where we considered classification problems. At the heart of these least squares approaches to these kind of problems was this inner product, x transpose times w. Note that I guess for the most time so far I have turned it around, that it was w transpose times x, but today I am deliberately writing it as x transpose times w. And yeah, the problem was to solve these kind of problems, and note that today I'm actually writing it in terms of the data matrix rather than the design matrix. Let me stress that. So for all that is to come today, that matrix X will be a column matrix, where every column in this matrix X indicates one of the training vectors xi we are given. And previously, when we looked at the least squares problems, I said, well, let's look at these design metrics. There was a row matrix. But today, for consistency with respect to the other algorithms, I can of course also express this least squares problem like this. This matches perfectly with this problem of having to compute in a product between x and w. Okay, and we have seen two solutions to this problem. Right? And once again, note that today I'm actually talking about data matrices, but if you put transposes over all the x, then with x transpose times x transpose, then that would be the solution in terms of the design matrix we have seen a lot of times. But this is now in terms of the data matrix, but this is exactly the solution, the primal solution for the least squares problem. And this matrix x times x transpose is an m by m matrix if the data is m-dimensional, including that additional dimension. This is the primal form of the solution, and we have used that, and you have used that in the exercises. But last week we saw that there is another solution to that problem. And whereas the solution we easily derive is given as matrix x times x transpose inverse times x times target vector y, this dual solution, which was not so easy to derive, reads matrix x times matrix x transpose times x inverse times target vector y. And whereas this matrix here is an m by m matrix, where m indicates the dimensionality of the data, this matrix x transpose times x is an n by n matrix, where n is the number of data we are given for training. And I want to point out that this matrix x transpose times x, now that we are talking about the data matrix and not about the design matrix, this is really, I'm sorry for this confusion, but you have to accept this. This is how the world is, right? It's very confusing anyway. If this x indicates the data matrix, then x transpose times x is what we call a gram matrix, which is to say that every entry ij of this matrix, x transpose times x, is just the inner product between vector xi and vector xj. This here is a matrix of inner products of the data we are given. This here is a matrix of outer products of the data we are given. This here is an m by m matrix, dimensionality of the data. This is an n by n matrix, number of the data. Quite often we have more data than the data have dimensionality. And I already said, like, why would we therefore ever just even think about considering this solution, because inverting this might be much more expensive than inverting that. And today we can finally understand why that would be interesting, because if we look at the kind of problem we are interested in, linear operations between data vectors and some weight vectors, and we have vector x transpose times w, and now we know that w can be written like this, so this becomes x transpose times w times matrix x times matrix x transpose times matrix x inverse times y. Then we recognize that if we use this solution for w rather than the primal one we have used up until today, if we use this solution, then everything that has to do with data, whether it's the new data or the data we are given for training, enters this expression in terms of an inner product. Right? Because here, matrix x transpose times x, I just said that the entries of this matrix are nothing but the inner products between the training vectors we are given. And here we have an incoming data vector x transpose times a matrix x, but that is to say we here have to compute the inner product between the incoming vector, now as a row vector, and all the data vectors we are given. This is what that says. In this form of the solution to our problem, all the x's we want to work with, and the xi's and xj's we are given for training, only appear in form of inner products. And here we see what it means to replace those inner products with kernels. Instead of matrix x transpose times x inverse, I just say, well, let's have some matrix K and invert that. And instead of vector x transpose times matrix X, this is a vector, right? This gives a row vector. Instead of this vector, let's have some vector K of x transpose, so that if we have K of x transpose, then we can multiply matrix K inverse times y. And the entries of this matrix, this will be a matrix of number of data times number of data, a square matrix, because once again this is a matrix of number of data times number of data, and so will be K. The entries of this matrix will be the outcome of some kernel function. So the entry Kij of that matrix K will be the function K of vector xi and vector xj. And this vector here, that will also be an n-dimensional vector, because here there are n columns in that matrix. Right? It has m rows. X is an m-dimensional vector, but this is an m by n matrix, so this will be a n-dimensional vector. The entries of this vector will be the outcome of a kernel evaluation of the ith training vector and the current input vector x. So if we consider the dual solution to the least squares problem, we end up with a classification function or regression function where the data is only present in form of inner products, and we can replace this matrix of inner products by a kernel matrix where the entries of that kernel matrix are the outcome of a kernel function. We can replace this vector here by a kernel vector where the entries of the kernel vector are the outcome of the evaluation of a kernel function. And now let's see what that buys us. And in order to see how to implement that in Python, I urge you to read this. This is not as urgent as reading the other two notes. This is just fun. Here is some data, and let's look at a regression problem. Well, it appears as if this data has been sampled, noisy sample from a third order polynomial. And indeed that was the case. I have generated a noisy sample of data from third order polynomial. And if we do kernel least squares for regression using the linear kernel, this one, then this is the model we get. If we use a polynomial kernel where magically I thought, well, let's use a third order polynomial kernel. You know, so this here is the function k I'm talking about. Right? Every entry in this matrix is the evaluation of this polynomial function for this matrix between the training vectors we are given, and for this vector k, it is between the incoming data vector and the training vectors we are given. If I'm using this third order polynomial on this third order polynomial data, then lo and behold, this is what we are getting. It actually fits the data. And then I can also, you know, be a bit bold and go for this Gaussian kernel. And this is what we're getting. It's not quite so good. But this is a very important slide in that sense. Tells you a couple of things, but you have a question.
This Gaussian kernel
Yeah.
tend to have a inner product between infinite dimensional vectors, so logically it should fit more perfectly than the third order polynomial kernel.
Yeah.
So
See, this is this is why I'm actually showing you these three examples. Exactly because these kind of questions, I cannot even count the number of papers I had to review where people said, yeah, use the kernel trick, and then because of computation time, we apply the linear kernel. This is easy to compute and does not cost much. Using this can actually be a computational overhead. It's not as easy, it's not as straightforward, it takes time to evaluate that. So I had to review hundreds of papers in my life where they claimed, yeah, and then we use the powerful idea of the kernel trick, and for computational convenience, we then use a linear kernel. This is what you get. You get nothing. And I could have told you in advance that you get nothing, because the linear kernel is exactly this. You don't gain anything except even more computation time. There is nothing to be gained by using linear kernels. Those people are retarded. No, seriously, they use something because everybody does it. Kernel methods are cool, right? Let's do it as well. Oh, it took so long until, I don't know, some result was, let's use a simple kernel. But you could have had that much, much cheaper with the same effect. Look at this. Linear kernel gives you that. A linear kernel is a linear function. You do not gain anything by using linear kernels except for even more computation time. So don't ever, if you resort to the kernel trick, use a linear kernel. There is no reason for that except probably when it comes to support vector machines. But in any other situation, it just does not make sense. And the same goes, like everybody says, yeah, and then we use the Gaussian kernel, because that's the most powerful kernel we have, in the sense of we know that this will be equivalent to inner products in infinite dimensional spaces. And yes, you are right, you have a lot of flexibility there, right? But that Gaussian kernel crucially depends on additional parameters, and the effect of these parameters will be noticeable with respect to the situation you're dealing with. And so therefore it is equally dangerous to assume that the Gaussian kernel will be the ultima ratio in any case. Right? And this is exactly the message I'm trying to convey here. Of course, this is once again a trivial example. And of course, you know, I knew that this is a third order polynomial, so it's a good idea to use a polynomial kernel with d equals 3. But it goes to show, and if I would have chosen different sigmas here, then different results would have popped out. But in this situation, it's really, I knew what the data was like, and so I knew what kernel to choose, and that will always give the best results. Of course, in general, we don't know that. And in general, it is a good idea to consider the Gaussian kernel, but maybe not. So careful there. This is really, you know, there are once again no clear-cut answers to that.
So that's why maybe people try to learn Gaussian kernel before using radial basis function or something, then apply them.
Yeah. It's a problem. Many people spend time on trying to automatically determine the most suitable value for this sigma. Yeah, it's a problem. But the one take-home message is linear kernels are forbidden. This is really like, you know, they are forbidden except for maybe in support vector machines. We'll see why in a minute. You have to know what you're doing. And the other take-home message is, what I did here really is, I did not, I don't know, compute a van der Monde matrix and then did sort of least squares on these polynomial expansions of the data. I did not do this. This has been computed with the original x vectors we are given, with the original data vectors where I attached this additional 1 to them, and then for the input numbers here, I turned them into two-dimensional vectors with this additional 1. But I have not computed a transformation of the data. I did not turn that into a van der Monde representation. I just replaced the appearances of inner products in the computation with the kernel, where the kernel was that. And the result is this. This is, of course, expensive, depending on how much data we are given. That can be very, very expensive. Like, say your data is two-dimensional, you have some regression problem, two-dimensional data, 50,000 data points. It might be smarter to, you know, go via the primal, turn that into some van der Monde matrix. Because here you have to invert a 50,000 by 50,000 matrix. This one will always be, I don't know, 11 times 11 if you're looking for 11-dimensional polynomials. Careful, right? If you use the kernel trick, stuff will become expensive, typically. You will gain a lot of flexibility, but it comes at a price. In particular, you know, if you have a lot of data, this will become very expensive very quickly. Let's look at what that buys us for classification. So in the following, we will always look at these two half moons, two-dimensional data points, obviously from two classes, omega 1 and omega 2, blue and orange. And this is certainly not linearly separable. So I train a simple least square classifier using, say, a polynomial kernel. First, where d is equal 1, that is a linear kernel. It does not buy us anything except it is even costlier to compute. But if I go for a third order polynomial kernel, things become to look like yin and yang. And with a sixth order polynomial kernel, it's like really like these twisty things appear. Does that generalize? I don't really know. Like from the point of view, like new data would come in. But these are the decision surfaces we get. This is basically implicitly the algorithm has mapped the data to some higher dimensional space, then done a linearly separate problem in these spaces, and I'm just sort of plotting a two-dimensional view of the outcome of that. So we have to be careful with what we see here. This is really just a two-dimensional view of the outcome of these algorithms, but it works. Right? Here I have used Gaussian kernels, and we see the crucial impact of the sigma. If it is small, then things look good. If it is too large, then things become distorted again. Right? So the Gaussian kernel is not necessarily always the best thing to use, and this choice of sigma is critical. And it may be very difficult to estimate an appropriate parameter for that kernel. Okay, now support vector machines. This will be the next one I'll discuss in detail, because that is sort of the original gangster when it comes to the kernel trick. Because here it's actually is really it's so straightforward. We don't have to look at dual things or whatever. I note that once again this is the dual problem of the L2 SVM training problem, and we have seen an algorithm for how to determine these vectors of the Lagrange multipliers. And I recall that the matrix G that appears in this matrix as one of the terms in this matrix was given like that. We had the label, so entry Gij of that matrix is label value Yi times label value Yj times the inner product, looked at this, between training data vector Xi and training data vector Xj. So for the support vector machine setting in training, we see that there is something in there that can be replaced by a kernel function or a kernel matrix. Right? And yes, it can. So we can easily replace this one with a function k of xi and xj. And then would have this matrix k over there. The rest remains the same. We replace this matrix with a kernel matrix, solve for mu. Once we have done that, I did not stress that last time. The thing is, for the L2 SVM, this bias term is a slightly different computation than I discussed last time, so I have to point out here. But once we have determined the Lagrange parameters of that problem, we can use the Lagrange parameters to determine the vector W we are interested in support vector classification. And we can use them to determine this threshold value W naught. And really, I didn't for the L2 SVM, just for this one. This is how we compute the threshold. Didn't stress it last time. If we have these, we can then use them to classify data, which is we want to compute a function y of x, which is just the sign of the inner product of x and w, plus, because of this different form, plus now for the L2 SVM, plus omega naught. Look at this. There is another inner product here. And we know that the W is just the sum over scaled support vectors, and the support vectors are from our training set. So we know them. And in order to compute the support vector machine classifier, we have to compute basically a scaled sum over inner products. In a training step, we replace the inner products by a kernel function. These inner products again have to be replaced by a kernel, or can be replaced by a kernel function. Right? So in support vector machines, this is very natural to do. Right? And this is where it first appeared, and then people kernelized everything. So the least squares example, we had to go through the dual, some not so straightforward solution, but once we had it, we could use the kernel trick. Here, the kernel trick is just natural to think of. Okay, that is to say we replace this matrix G that appears in training with corresponding kernel evaluations, and we replace these inner products that appear in the application phase of the classifier with the kernel evaluations. And here are a couple of support vector machine results on this data. Once again with the polynomial kernels, and then once again with Gaussian kernels. And also note that I'm also presenting the value of this parameter C that somewhat gives the sensitivity to the problem of points lying on the wrong side of the separating hyperplane, which will now be a hyperplane in a very high dimensional space. Right. This actually has been done, the data has been implicitly mapped to an infinite dimensional space, and in this infinite dimensional space there is some hyperplane, and that hyperplane is used to classify the data, and then I've just colored all the pixels in these images according to the outcome of the classification. Yeah, for the polynomial kernel, works well. Look that I'm actually indicating the support vectors today. Those are the ones with the tiny square brackets surrounding them. Tiny squares, black squares. Yeah, what is there to say? Except for probably like that here we see if we choose the sigma too small, then this will definitely not generalize well. It does the job on the training data, but if new data comes in, we don't know what will happen. Yeah, but if I would have chosen it too large, note these are all very small values for the sigma. If I made it larger, then it would have become useless again. So, and also I had to experiment with this value. So there's two parameters when it comes to support vector machines and Gaussian kernels, and which parameters to use. This is an art. This is an art rather than a science. There are no general answers here. And it may be expensive to determine these things in practice. But it can always be done, but you have to know that. Now, since we had so much fun with the support vector machines last time and 13 lines of Python code, let's repeat this, but now with kernelized support vector machines, right? So I actually spread the Python code over 3 slides. Here, this is just say you are given some data matrix, and I assume it's a column matrix. So you have a couple of data vectors as the columns of a matrix X, and you have a corresponding label vector, Y, and important for this support vector machine setting, we assume that these are really plus or minus 1 values. Right? But you are given data matrix X and label vector Y, then we can magically train a support vector machine, say with a polynomial kernel, and that gives us the vector of the Lagrange multipliers. Here we look then for those Lagrange multipliers that are larger than 0, for the active ones, for the ones that indicate the support vectors. So I basically collect the indices of the entries of this vector m of Lagrange multipliers where m has a value larger than 0. And I use these indices to determine the support vectors, which are those vectors in matrix X for which the Lagrange multipliers are greater than 0. Do the same with respect to the label values, and I actually also collect the values of the Lagrange multipliers for those that are larger than 0. And once we have the support vectors, the labels, and the corresponding Lagrange multipliers, we can then compute this offset thing using this equation we've seen earlier. And then there is a matrix of test data on which we want to apply the support vector machine. There is a function apply support vector machine, blah, 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 and then that will give us some result. Then we just look at the sign of that and we are good. Now the interesting thing is, of course, this function train and this function apply. And once again, given what we have studied last time, this is really just a couple of lines of Python code. The only difference to the training procedure for the support vector machine we looked at last time is the matrix M we consider in this problem. Look at it. So the problem we have to solve is this one with respect to mu. And last time we actually really solved exactly this problem. And today I'm replacing this matrix with a kernel. And this is the only difference. And so therefore, the difference is here. There is a kernel, which happens to be this polynomial kernel, because this is easy to compute. Gaussian kernel is really slightly more tedious. So basically we're given the matrix of training data, compute the inner product of this matrix with itself, matrix x transpose times x, add a constant b, raise that to some power d, and we have a kernel matrix. Using this kernel matrix, we can then have this matrix. Now I call it M, last time I called it G, that was stupid. So M is basically this outer product of y times k plus this outer product of the vectors y with this scaled identity matrix, and then we enter the Frank-Wolfe iteration here to solve for an appropriate vector of Lagrange multipliers mu. It's another thing, last time I initialized that with 1, 0, 0, 0, 0. Today it is actually 1 over n for all the entries. It gave better results in my experiments. So this is how we solve for this vector mu of Lagrange multipliers now, today, using a kernel. But other than that, everything remains the same. Once we have that kernel, or the support vectors, like once we have solved for mu, we can compute the support vectors, we can compute this threshold value, W naught. This is how we would apply this now. In the first line, I basically check if the input data we want to classify is a single vector or is actually a collection of vectors. If it's just a vector, then I have to reshape it, blah, 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 long story short. Here's how we compute the kernel vector, which is just the inner product of the input vector or matrix of input vectors we have with the support vector matrix. We once again add this constant b, raise that to some power d, and we have our kernel vector. And then we just have to sort of scale every entry in this kernel vector with these values of the labels of the support vectors and the entries of the active Lagrangian multipliers. Have to sum that and add this threshold value. It has to be added here because it's an L2 SVM. Add that and we're done. We return that and look at the sign of that, and this is what we get. Right. I'm showing you this one here. This is basically exactly the same 2 half-moon data, but whereas it was 200 data points in the previous example, this one is with 2,000 data points in total. And I've tested it on like the whole image, every pixel here. If you count that as a data point, that would be 134,500 data points. And training and testing under this setting took less than a second. I'm a bit braggy here. This is of course because of the Frank-Wolfe algorithm. It's such an efficient idea. When I first used support vector machines like 15 years ago, that unheard of. It's like 2,000 data for training is not much. Is not much, really. This is not a big data setting. But still, training this with 2,000 data points and then applying it to more than 100,000, it took, less than a second using NumPy. And there's progress after all. 15 years ago, that would have taken some time. This is how you can train your own kernel support vector machine. And note once again that I have done this example with respect to the polynomial kernel because that is fairly easy to do and fairly efficient to do. The Gaussian kernel is slightly more elaborate and expensive. Okay, now we enter a couple of slides I will probably not really discuss. Once the kernel trick was understood in machine learning and pattern recognition, that was about 15 years ago, a frenzy set in, and it became a favorite pastime and sports among computer scientists to kernelize everything. And indeed, everything can be kernelized if we can express the corresponding algorithm in terms of inner products. Here is the linear discriminant analysis problem. Our problem is to determine this optimal projection vector W star, which is the minimizer of this Rayleigh quotient, which is actually boils down to matrix SW inverse times mu I minus mu 2, where SW inverse is the inverse of this matrix. Mu I and mu 2 are the two class means of the data. We're given this a binary example once again. We can kernelize that, and I will not discuss how. Those of you who are interested in that, read this, read this, read this, and this. Let me really, this looks crazy, but this is just linear algebra. This is really just plugging stuff into stuff and multiplying matrices, and there's really. The long story short is we can kernelize linear discriminant analysis. Actually, it really can then be expressed in a sense in a dual kind of way. It's not a real dual, but can be expressed in terms of a vector of coefficients rather than in terms of a projection vector. The solution looks suspiciously similar to the original solution, but this is now in vectors of the dimensionally of the number of data rather than of the dimensionally of the dimensionality of the data. This is how we would compute the classifier, and if we do this, here are examples of what kernel LDA could do for us. Not really worth talking about. We can also kernelize principal component analysis. And to this end, we recall that in traditional principal component analysis, we are given a data matrix. We compute the covariance matrix, which note is the outer product of this data matrix with itself. And we are then interested in the solutions to these eigenvector eigenvalue problems. Once we have the eigenvectors and eigenvalues, we use them for further processing. Here is once again this algebraic mumbo jumbo, where we express the original problem in terms of not the dimensionality, or not in terms of vectors, the dimensionality of the data, but in terms of vectors of the dimensionality of the number of data. Note that we can say, well, the covariance matrix times u equals eigenvalue lambda times eigenvector u. Instead of the covariance matrix, I can write 1 over n, x times x transpose, and I can divide by lambda. And then I will call this vector, which results from multiplying matrix x transpose to u, scaled by this. So this scale factor times this here is called alpha now. And that is to say, just algebraically, this is mumbo jumbo, but it really works. This just goes to show that the solution, an eigenvector, can always be understood as a linear combination of the data we are given. So this is the data matrix, and then there is a n-dimensional vector alpha, and so every eigenvector is indeed some linear combination of the data we are given. And of course that will be a different linear combination for different eigenvectors, but every eigenvector is nothing but a linear combination of the data we are given. And we can then use this representation to sort of consider principal component analysis once again in the dual form. And to this end, we really just replace the u's by matrix x times alpha. And a lot of algebraic mumbo jumbo and some substitution, lambda tilde equals n times lambda. It turns out that this original eigenvector eigenvalue problem can be cast as an eigenvector eigenvalue problem with respect to a matrix of the dimension of the size of the data. Here there is this extra process, actually square this, we now divide both sides by, or multiply both sides by the inverse. K is once again a kernel matrix. Right? And we can of course replace this kernel matrix where we now have in the original form all the inner products between the data vectors we are given. We can replace those inner products by some kernel function. I also have to point out that there has to be a strange normalization has to be done, can be done. And then there is something else we have to do. We have to center those kernel functions because I'm not discussing that. This is bug free. You can read it at home. When we do principal component analysis, remember that we have to turn the data into zero mean data, right? And we are given some data. Where is the data? There's the data, and now we implicitly do this in some higher dimensional vector space. And even if the original data is of zero mean, there is no guarantee that in this higher dimensional space it will be of zero mean. But we have to make sure that it is of zero mean, and we can actually really do this just with respect to the kernel function. Not going to discuss this, but if you're interested, look at this. Instead of discussing that, let's look at the crazy results we get when we do this. Here's basically the recipe we would do when we do kernel principal component analysis. And now, things are going to become psychedelic. Here we see a collection of two-dimensional data points in a two-dimensional space, and here is another collection of two-dimensional data in a two-dimensional space. The first one happens to be a Gaussian blob, and the second example is a collection of Gaussian blobs. And what I'm showing you here is just to warm up for what is to come next. Now I can compute traditional PCA on these two-dimensional data vectors, and I will get two principal components. Because it's two-dimensional data, there will be two eigenvectors. The first one for this example is this one, and the second one is this one. And all makes sense. Right? The one, I have actually scaled them using the eigenvalues, and that makes sense. Both vectors are actually unit vectors, but I've scaled them using the eigenvalues. So indeed, we recognize along this axis there is the largest extent in this data, and then this one is perpendicular to the first principal axis, and the variability in this direction is not quite as large. And what we see in this first row is the colors in these images represent the value of, say, this vector here, some point here, projected onto this eigenvector, and the larger that value is, the bluer the color will be. So if we look at some point over here, and I project it onto this eigenvalue, this will give a negative number. The projection onto this vector for this vector here will be something negative, something small. The redder a pixel is, the smaller is the projection onto that eigenvector. And here we see the same situation with respect to the second eigenvector. The bluer a pixel is, the larger is the value of the projection of the corresponding point in 2D along this eigenvector. And the redder it is, the smaller is the projection of this vector onto the eigenvector. And look at this, is perfectly, this is basically a gradient from red to blue, a gradient from red to blue. It makes sense. And we have the same effect for this not so natural data when it comes to principal component analysis, because this is, it does have eigenvectors. They always have, like every collection of data, has an intrinsic coordinate system. But here it is not so clear in comparison to the original usual Gaussian blob. like in how far these eigenvectors actually indicate something about the data. Right? If the data is a Gaussian blob, then those eigenvectors really indicate the principal axis of these data. Here they of course also indicate the principal axis of the data, but it's not as easily to interpret as it is over there. But once again, the redder something is, the smaller is the projection of that corresponding vector along the corresponding eigenvector. And once again, we have a gradient from red to blue and a gradient from red to blue. This is done with traditional principal component analysis. This is done with kernel principal component analysis. And I had to go through the previous slide to explain the coloring scheme. The coloring scheme is exactly the same. The thing is that I have done this with the Gaussian kernel here. The eigenvectors are infinitely dimensional. I cannot plot that, but what I can plot is the value of the projection of a correspondingly transformed data vector with the corresponding infinite dimensional eigenvector. The bluer something is, the larger is that inner product, and the redder something is, the smaller is this inner product. I did not compute these inner products. I computed kernel functions. But these kernel functions do inner products. Right? And I therefore can evaluate these infinitely dimensional inner products. And this is what I get. And this is really funny for those of you who, again, were with me in image processing. That looks suspiciously like Gabor filters. You know, it does. And it is an artifact of the fact that the data I considered here is actually a Gaussian distributed data sample. But now, let's look at the three blobs. This is once again projection of all the pixels, like two-dimensional data points implicitly transformed to infinite dimensions, implicitly inner product computation with infinite dimensional eigenvectors. The bluer something is, the larger is the value of this inner product, and the redder something is, the smaller it is. Look at this. This kernel principal component analysis is a clustering algorithm, because it distinguishes this blob from these two. This is the first projection along the first principal component. And it clearly sort of signals out this as very positive and these as very negative. And the projection along the second principal component then realizes that this here separates into two clusters again. It identifies these as very positive and these as very negative. And for the remaining one, I don't know what happens. Nobody knows. It's in infinite dimensions. But this is a clustering algorithm. And for those of you who have already worked on the projects where you have to do this spectral clustering.
We need to take the second.
Pardon?
We need to take the second.
Yeah, there I said take the second smallest one and look at the value of the entries, but this is not, the issue is not like which eigenvector you take. The issue is, think about what kind of a matrix it is you compute when you do spectral clustering. And probably put that into this context here with the K thingy. I said for these pictures I use the Gaussian kernel. I don't know what I wanted you to use in the projects, but yeah. Gaussian, yeah, okay. Put that into context now. It's there you have to look actually for the second smallest eigenvector and look at the entries. It's different than what I'm showing you here, but think about those matrices and this matrix here. Okay, then kernel k-means clustering. I don't have to do that, you can do it by yourself now. If you go through all these slides with how to replace stuff by inner products, I don't have to do this. But what I have to do is to really hit home why these kernel methods are so interesting. With all the examples we have seen so far, it's just, you know, some Euclidean vectors, some transformation to some higher dimensional space, and yada yada, like nonlinear problems, and that is all good and well and very, very nice and good to know and good to use. But there is something else entirely we gain from knowing about kernels. And that has to do, for instance, with data like that. This is the first time, not quite, we had done some Markov chains. Second time in this whole lecture series that we are looking at a data set that is not composed of Euclidean vectors. Well, it's a data set nevertheless. It's actually Homer Simpson, Marge Simpson, Bart Simpson, Lisa Simpson, and so on. You know who these guys are, right? But it's a data set of strings. How do we analyze data like that? How would we cluster data like that? Is there a way for us to use all the algorithms we have learned about so far on non-numeric data? Now, the obvious answer given today's lecture is, of course, yes, there is. Yes, there is. These are non-numeric data. They do not create a vector space. Strings just don't have the properties we would require from things that make a vector space. Strings do not have these properties. There's no discussion about this. And nevertheless, there's hardly any data out there for which we cannot come up with a measure of similarity. For instance, one way of measuring the similarity of two strings is n-gram similarity. Here, for the string Homer Simpson, I have computed all the bigrams. So this is H-O-O-M-M-E-E-R, R blank, blank S, S-I, I-M, and so on. So those are the bigrams of the string Homer Simpson. I could have computed 3 grams or 4 grams, n grams in general, but we can do this. Like if we split the string into all its n grams, we can do this for one string and another string, and for instance compute this, is it called Jacquard index? I don't know. There's so many different things you can compute there. But this is a measure, one possible measure of the similarity of two strings. Syntactic similarity, I should say. Right? Like we intersect the two sets of bigrams, multiply that by norm of that intersection set by 2, divide by the sum of the norms of the two sets of bigrams. We can turn a similarity into a distance, like if you can convince yourself that this value similarity of two strings S1 and S2 will always be a number between 0 and 1. And it will be large if the two things are very similar, and it will be 1 if the two things are very similar, like exactly the same, and it will be 0 if they are like totally dissimilar. We can turn similarities into distances, for instance here by just computing 1 minus the similarity, because then it will be 0 if they are the same and 1 if they are totally dissimilar. And now we have a distance, and there is nothing, seriously nothing, that would prevent us from replacing a Euclidean distance in a Gaussian kernel with any other distance. There's nothing. Right? In fact, also convince yourself that instead of having to use this, I could have sort of computed a kernel using the similarity right away. Because if we replace the similarity by distance and then plug the distance into this, then it will be a similarity again, right? Because 1 minus e to the minus 0 is 1, and so actually I could have avoided this deviation via this here and have used the similarity thing as a kernel right away. This is just to show you can think of any kind of similarity measure between graphs, between strings, between genome sequences, between anything. There is no practical problem to define a measure of similarity between stuff that is not, which are not elements of a vector space. We can always invent some notion of similarity. If we have a notion of similarity, we can always turn that into something akin to a distance. If we can turn it into something akin to a distance, we can plug it into a Gaussian. If we can plug it into a Gaussian, we have a kernel. So here is a collection of non-numeric data, and this is, I don't know, 48 or so strings, and I have computed a 48 by 48 kernel matrix. And then I have done principal component analysis with that kernel matrix. And then I have followed up on this recipe here, computed basically this expression for the first 2 dimensions of the resulting infinite dimensional principal component vectors. And this is what we get. Here is the Flanders family, Rod and Todd and Ned, Flanders, very syntactically similar strings. Here is the Simpson family, all their last name is Simpson, Homer, Bart, Lisa, Maggie, Marge, A, and the rest is somewhere else. Kernel principal component analysis is a clustering algorithm. And it applies to any kind of data for which you can define a convincing kernel function. And if you compute projections into other dimensions, you get other clusters here. And it was a lot of fun for me to do, but I'm not showing them here anyway. This is the real power of what we have learned today. We have now a handle for how to deal with non-numeric, non-vectorial data using all the techniques we have learned about. I could have used this here for kernel LDA on these strings. Could have, I don't know, tried to learn a classifier. Or could have used kernel least squares to train a classifier. Or could use kernel least squares regression to regress some function over these strings. That can be done. The kernels provide us with great flexibility when it comes to nonlinear numeric data, but they also open the door towards any other form of data out there. That is the real power of the kernel trick. And this is all I have got for today. Yes, you have a question.
It's not only because of kernels we can apply it to strings. Because you got the metric for strings.
Mm-hmm.
If you got this metric, we can apply neighbors.
We can. Okay. So yes, once you have some notion of similarity or distance,
yes,
you can always have an n by n matrix that gives you a relational representation of the data you're dealing with. That is, you can always come up with a graph or a network, depending on what term you prefer, let's say with a graph representation of relations between data items you're given. Once you can do that, you have a lot of power. You can do a lot of things. And of course, it is not only kernel techniques you can apply there. In that sense, you are right. But the great thing with the kernel thing is that, in a sense, you know, this just gives us a sort of a adjacency matrix, a relational matrix, right? But the great thing with all these kernel methods is that now all these techniques we have studied become applicable. Of course, there are other things that also become applicable, but once we understand those things in terms of kernels, we can do linear discriminant analysis, support vector machines, stuff like that. Of course, you can do, I don't know, graph partitioning and lots of stuff. but this here really opens the door towards dealing with non-numerical data using all the techniques we have studied. And that is really, this is, even though the support vector machines have dropped from popularity, do not underestimate the importance of the existence of the kernel track. This really, even though nowadays everything is done with neural networks again, these things in biology, when it comes to genome sequencing, this has been a revolution. Really, this is good stuff. We have learned about the notion of Mercer kernels and the kernel trick. And because the kernel trick is so important, I actually rephrase it here. Kernel trick is to first rewrite an algorithm for analysis or classification such that input data only enters it in form of inner products. That may require some gymnastics, some mental gymnastics, but for a lot of algorithms we actually can do that, and we've seen a couple of examples. Once we have rewritten the algorithm such that the input data really just enters it in form of inner products, can then replace those inner products by kernel functions. And we have seen a couple of examples for what that buys us. In particular, we have looked at kernelized versions of a couple of algorithms we have studied earlier. That is all I have for today. And that was, again, a lot of stuff, and I typically would have spread that over at least 2 lectures. But this here really is the important thing. You need to be aware of it, and really just don't be aware of it from the point of view, yeah, we can deal with nonlinear problems using linear techniques. You can also deal with non-numeric data. Do you have any questions? Great, then see you next week. Thank you.